works great.
Do you mind if I...
Yep,
take about 2 minutes? Yeah.
I'll find over here.
So, good morning everybody, and welcome to the first ever Embedded Linux tutorial that is happening in the Embedded Linux conference. It's the first year that we organize tutorials the day before the conference, and we have the pleasure to have Chris Simmons with us today for the Linux tutorial this morning, and maybe some of you will also attend the Android tutorial in the afternoon. You'll probably say a few words about the logistic, right? Or shall
yes.
I do it?
Well, you did, 'cause
yeah,
I'm not sure
so,
I fully understand it myself,
yeah,
so
yeah.
I'll listen and then I'll complete it again later.
So the tutorial this morning, the Linux tutorial goes from 9 to 12:30, right? With a break at 10 a.m. if I'm correct, because we were supposed to have coffee at 10, if I understand correctly. And the Android tutorial will be in the same room at 2 o'clock, and ending, God knows when exactly.
5:30, I think. 5:30. About 5:30.
All right. So again, I mean, welcome. I hope you'll enjoy the tutorial, and we'll be pleased to have your feedback at the end and tell us if this is something that we should renew in the next edition. Thank you very much. Have a good day. Oh yes, and one last remark. Some of you are not yet registered because we were running out of time, so you can always register whenever you want during the day. It's absolutely no problem. Chris?
Okay, thank you. Right, well, good morning. Welcome to this tutorial on a quick start to embedded Linux. Just before I go on, let me just comment that we've got a lot of power cables trailing around here, so whenever you're moving around, please be very careful that you don't trip over and sort of yank everybody else's laptop off the table. That wouldn't be very popular. And also, if you can kind of keep your bags and such like under your seat or in the luggage. No, we don't have any luggage compartments, unfortunately. Emergency exits are over there and over there. Tea and coffee will be served at some point. So there we go. Let me just give a quick overview of what I think this is about. I've divided it into 3 45-minute presentations because I reckon people can't really sit still for more than 45 minutes and pay attention, so that's my kind of limit. Plus that's about as long as I can talk for. The first two actually, there'll just be a very short gap in between them, so we can take a quick break, a very short one. And the idea is I want to have a talk about Linux as an embedded operating system, and the good things and the bad things about it, and in particular the challenges you have in adapting Linux as your embedded OS. So I'm going to start off with, in the beginning, we're going to talk about the genesis of a Linux project, and I'm going to talk about the 4 basic elements of embedded Linux, which are the toolchain, the bootloader, the kernel, and the root file system. And then I'm going to talk at length about those 4 things, because until you've got those 4 things in place, you can't really go on to the next stage. And then we've got a break when hopefully coffee will be served. Come in if you'll just grab a seat. And then we have got, and I'm sure this is the real reason you're all here, not to listen to me, but you'll each receive one of these USB sticks modules, which have an ARM9 processor on and so on and so forth. So I'll talk in more detail exactly what this thing does and how you can use it. And then finally, for as long as we want to go on for really, up until lunchtime, you will then have a chance to play with these things, and I have some instructions on how to set them up and how to compile a kernel for them and all that stuff. The slides are available on a website somewhere, and I'll give you the link later on. And also, you'll need to download, of course, the notes that you'll be going through. But apart from that, I'm afraid it's down to you to make notes on the pads if you feel that you need to make a note, of course. What else? Other details. Ask questions as and when. It's a reasonably large group here, but I think we have time just to take questions as they come along. I don't particularly like saying leave your questions until the end, because by the time it gets to the end you've forgotten what the question was or whatever. So, plus it turns out if you haven't understood what I said, which is quite possible, it's very likely that nobody else understood it either. So it's always good to sort of make you back up and explain things. Another point, it would be good if you could set your mobiles to silent, or maybe turn them off completely, so we don't have distractions, at least while I'm doing the talks. Right, good. So first question then, how many of you, so we have a quick show of hands, how many of you are using Linux in an embedded operating system, well, in an embedded project right now? So, 2/3, 3/4 maybe. Good. And is it going well? Almost finished? Or still? Well, hopefully I'll help give you a few hints as to what are the things to look out for, and also show you how the building blocks all fit together. Okay, right, off with the start. Right, in the beginning. As I said at the start, I want to talk really about these four elements, the four key things you need for an embedded project: a toolchain, a bootloader, a kernel, and, well, I've put here user space. Root file system is what I really mean. So in this presentation, I want to give the overview of this, and then I'm going to talk about the first two elements. So, the genesis of an embedded Linux project. Usually somebody comes along, your dear boss or somebody, and says, I really think we ought to be running Linux on the next version of our product. And then you, as an engineer, have the task of making that happen. I've seen this scenario many, many times over. So what I want to look at is, from the engineer's point of view, what the hell do I do at this point? How do I make this work? I should say the reasons that our dear bosses want us to do this kind of thing, well, sometimes it's engineering-led, actually. Sometimes there's just functionality in Linux that we can't get any other way, or not sensibly. And in fact, in my experience, that's the main reason why people use Linux. But the other reason, of course, is the one that attracts the bosses and the accountants, is that it is quotes free, unquotes, by which they mean you don't have to pay for it. And that's a powerful attraction as well. But I'm mostly interested in the technical side of things. So, the four elements of an embedded Linux system. Now, at this point, I was thinking to myself, I need something that matches the idea of fourness. And I thought, well, Fab4, Beatles, maybe, but no, maybe not. And then I thought, I know the four elements. So apologies for this, I'm not going to make a big thing about this, but I thought, well, the four classical elements. So I thought the toolchain would be air, because it's kind of all around, it makes everything else breathe. Everything else depends on it. The bootloader, since it's at the bottom, obviously is the earth, so that kind of makes sense. The kernel is the fire, that's the thing that makes everything burst into life. That's the engine that drives everything along. And then user space is the water. It flows, it makes everything look nice and smooth. Whereas you know that underneath that beautiful glistening surface, there's a whole messy mess of rocks and seaweed and such like. So the user space covers everything else up and makes everything look nice and smooth and pretty. So there you go, I thought that was quite clever. Right, starting off then with the toolchain. This is always the first point of any Linux project, or indeed any project of any sort in actual fact. Until you can generate code for your target platform, you obviously can't do very much. Toolchain consists, as far as I'm concerned, of these four things. We're talking about GNU toolchains here, of course. So you need a package called binutils. Binutils, binary utilities. This has the assembler, the linker, really anything that has to do stuff with object code. So you need to get hold of that and have a version that's, that will generate code for your target. You will need a C compiler, because most of what we're going to be talking about today is written in C code, including kernel and most user space, basic user space stuff. You may want other languages as well, but you will always at least need a C compiler. The C compiler requires a C library, libc, because the C library is the interface between applications and the kernel. The Linux kernel has a C language binding. Now, there's one good reason why you need a C compiler. And then the fourth element, the debugger, GDB, the GNU debugger. Now, you only really need this, of course, is if you're going to have bugs in your project. So if you're not planning on any bugs, you can leave this bit out. But it's probably best to have it. At the very highest level, there are two ways of putting together a toolchain. The simplest is to have a native toolchain. In other words, you have those four elements I just mentioned, those four parts of the toolchain, and run them on your target hardware. Now that's fine if your target hardware is powerful enough, has a powerful processor and enough storage and memory. But most embedded targets do not. However, you can still sort of achieve that effect by using an emulator, QEMU, which can emulate a fair range of different processors, including ARMs and PowerPCs and MIPS and such like. The idea is that by running the emulator on a PC hardware, you have access to all the RAM and, well, a fair proportion of the RAM of your system and storage and such like. And even though it's emulated, it still is likely to be faster than your target processor. So that's one option. The other option, the more traditional way of doing things, is to have a cross-development environment, where you run the tools on, for example, your PC, and they generate code for your target board, or whatever that might be. This is what most people do, and this is how I'm going to describe the project throughout the next few slides. Whilst we are talking about toolchains, we need to talk about C libraries, because the C compiler and the C library are fairly intimately linked, and typically they're generated at the same time. So at this fairly early stage, are you here for the tutorial?
Yes.
Come and grab a seat.
Come in.
There are a couple here and a few over there. You'll just have to.
Yeah, you can.
Is that door wedged? Good, good. Yeah, so at this fairly early stage, you're going to have to make a decision as to which C library you want. Which is a bit of a pity because that's quite fundamental. Well, there are 3 C libraries that are in common use for embedded systems. The most obvious is to use the standard GNU C library, glibc. And indeed, that's what we will be doing in the practical part of this tutorial. The only snag with glibc is that it is quite big. So it's not suitable for systems with a small amount of storage. Fairly recently, which I mean over the last couple of years, there has evolved a variant of glibc called E-glibc, the embedded glibc, which essentially is just glibc, but it's more configurable, it's easy to cross-compile, and it's therefore more embedded friendly. By more configurable, I mean you can actually chop chunks out of it. If you don't want a certain area of functionality, you can just leave that out and create for yourself a smaller library. So that would be a good choice as well. Unfortunately, embedded toolchains tend to lag behind the mainline somewhat. So it's we're only just getting to the point now where embedded toolchains are using eglibc as a default. But I was a little surprised to realise when I was researching this a couple of days ago that in fact Ubuntu and indeed Debian use eglibc. So right now on my laptop I'm running eglibc, not glibc. And they did that since 9.10. So that goes to show that eglibc works and it's mainstream and that you can use it for a main desktop system, a real system. And then the third one is one called UClibc. This is the microcontroller libc, which was generated, well, the project is managed by roughly the same people who do the micro C Linux, UC Linux version. And so UClibc has support specifically for UC Linux, although it will work on ordinary Linux as well. I have a bit of a love-hate relationship with UClibc. By and large, I would recommend that you don't use it, because it is a subset of the C library. It misses out, well, it doesn't have an up-to-date threads library. It uses the older Linux threads, which is not so good. It doesn't have all the POSIX functions that have been put into glibc over the last 5 years or so. Things like POSIX message queues, shared memory, POSIX shared memory, and so on and so forth. And it lacks real-time functions. So it doesn't have priority inheritance mutexes, for example, which is something you really need for, at least for a real-time embedded system. So the only times I would use UClibc are either because I'm using UC Linux, in which case it's practically the only choice, or I have a system with less than 16 megabytes, say, of storage, which is fairly rare these days. So today we're going to be using glibc for our toolchain. I would tend in the future, if you're starting out on a new project right now, to look for an glibc based toolchain. What other criteria are there for selecting a toolchain? Well, the most fundamental thing, of course, is that it should support your processor. And not only should it support it should support it well. So my example here, if you're using an ARM Cortex A series, Cortex A8 for example, then that it uses the instruction set ARM v7t. So it's the ARM instruction set version 7 with interworking. So that's the ideal compiler to use with that processor. But because ARM processors are backwards compatible with previous versions, you could actually use an ARM v4 compiler and it would work absolutely fine. It just wouldn't be using the maximum benefit of that processor. And so, for example, if you use Debian ARM is compiled actually for ARM v4t, which is ARM v4 plus interworking. So you can use a Debian ARM toolchain with a Cortex A series processor, but you're not getting the full benefit. You'd be much better off using a different toolchain. And I'll give some examples in a moment. So make sure not only does it support your processor, it supports a particular variant of your processor. Secondly, we've talked just now about C libraries, so make sure that it's compiled with the C library that you think is best, which in my opinion is glibc. Make sure it's up to date. I'll talk about this in a short while again, but a lot of embedded toolchains that you will find links to on various websites, they are in many cases quite a long way out of date, by which I mean 5 years or more out of date. And they still work, of course, but it is better to have the latest versions of things with hopefully bugs fixed and hopefully new features added. Have a look at the support. If you are obtaining this toolchain from a commercial organisation, then ask them what level of support they're going to give you. In particular, are they actually going to keep it up to date? Coming back to this point here. Or have they just given you a toolchain with a board and they're just going to forget about you? If you are getting a toolchain from a community-based project, such as Open Embedded, for example, then again, have a look and see what their support policies are. Will they keep it up to date? Will they give you bug fixes, etc., etc. All of these things you need. And then optionally, there may be other things that you would like in your toolchain apart from just a C compiler. Very, very useful is to have a good repository of cross-compiled both libraries and utilities of various sorts. So you don't have to cross-compile everything yourself, which, as I'll mention later on, is a real pain. And also development tools like tracing and profiling, memory leak detection, that kind of stuff. These are all good things to have. And then if you really like these kind of things, you can maybe look for plugins for Eclipse or other development environments. Okay, but I guess the point I'm trying to make here is this is a big decision A lot of times it seems to me that people just fall into using a particular toolchain without really putting any thought into it at all. Usually most people just take the simplest, least path of least resistance. Don't do that. This is crucial. You have to get the toolchain right for the rest of the project to work correctly. So don't just take what seems most obvious. This slide and the next, apologise for the relatively small writing here. Like I said, these slides are available. I'll give you the link later on. But this is just going through a number of fairly common choices for toolchain. So starting over here, excuse me, we have a company called Co-Sorcery, based not too far from here, I believe. And they do commercial toolchains, but they also do a free toolchain called G++ Lite. Now, it's a very high quality toolchain. The guys at Co-Sorcery know a lot about cross-compilers and how to create these things, but it is a minimal toolchain that you'll get from them. It is just the four things I mentioned. It's the binutils, the C compiler, the libc, and a debugger. So if you take that choice, you've got quite a lot of work to do to fill in the gaps. This group here are a collection of binary toolchains for various processors. The one we'll be using is from the Angstrom distribution, which is a community-based toolchain, and it supports a fairly wide range of processor types, especially ARM. It supports all the various ARM architectures, so it's a very good choice for that. If, on the other hand, you are working with PowerPC processors, the DENX ELDK, Embedded Linux Development Kit, is a good choice, because the guys at DENX are very good at supporting PowerPC processors. So these guys have better PowerPC support, these guys have better ARM support. And then in the middle I've got a couple of mainstream distributions, Debian and Ubuntu, both of which do ARM variants, and Debian also does PowerPC, and quite possibly some others I didn't really check. One difference between these two, actually, which I haven't noted on the slide, Debian only support the ARM v4 instruction set. Ubuntu only support the ARM v7 instruction set. So the Debian will work on practically any ARM processor, though not necessarily making the best use of it. Ubuntu ARM will only work on a Cortex-A series. So those are some choices. The nice thing about these is they're binary, so you don't have to compile anything. You just download these various things and you can be up and running in a very short space of time. And hopefully some of you at least have downloaded a version of the ARM cross-compiler or need from Angstrom. More options. If you want to delve a little bit deeper, instead of using a binary distribution, you can get one of these integrated build environment tools, such as Buildroot, Open Embedded, LTIB. And essentially these will, they all have some kind of configuration mechanism. So you'll go and run that and select which compilers you want, or which targets you're going to compile for, various other development libraries you may want. And then typically you just type make, and then it will download all the source code and cross-compile everything and put it all in the right places. Morning, Klaus. Good morning. Don't mind me.
There are 2 seats available over here.
So these in some ways are better because They give you the source code. I mean, obviously you can get the source code for the other things as well, but this gives it to you up front. And it means you've got a bit more flexibility as to exactly what you compile. The only downside, particularly with Open Embedded is that the basis actually of the angstrom distribution that we will be using. Open Embedded has quite a steep learning curve, but it's very powerful once you've mastered what the hell is going on. And then finally, in this area down here, I've got some commercial offerings. Monte Vista, TimeSys, Wind River, LinuxWorks, and Cisco, amongst others, will all sell you a package consistent of the things I've discussed so far. But the key thing these guys give you is support. Paid for support, commercial support. Which in essence means that when things go wrong, you can pick up the phone, or more likely send an email, and shout at somebody. Which always makes you feel better, I find. Question at the back there.
Yeah, could I have your opinion on how Open Embedded compares with the commercial? You know, are they comparable? In the tool chain, in the tool chains. I mean, you said Open Embedded is powerful. I mean, compared relative to what? Because I've been using Open Embedded for a few years, and it's a steep learning curve, all right, and it's not straightforward. It's pretty complicated when you get into trouble.
This is very true, yes.
You know, and I'm just wondering, is it worthwhile persevering with Open Embedded, or is a commercial product, does it do more than Open Embedded?
I'm trying to work out how to answer that best. I mean, in essence, you've got to make your own choice.
Yeah.
But for myself, I would always choose Open Embedded. Is anybody in the room from any of these guys? Can I talk to them? I know there's some person on the internet. It swings and roundabouts. If you want the nice, comfy, handhold feeling sort of thing you get from these guys, then go with them. And like I say, the main thing you're buying, let's be clear, is support. The ability to email somebody when things go wrong. That is the key thing you're getting from these people. So if that's what you want, or if that's what your boss wants, go with it. But you will find that the tool chains these guys ship are quite old. They don't update them that often. They usually ship quite old kernels. So in essence, they're not really up to date. They don't really follow the current main line for both tool chains and kernels and so on. And also, they are somewhat restricted on the tools and libraries that they will offer. Whereas with Open Embedded, for example, you've got several thousand packages to choose from. From these guys, typically you've got a few hundred. So my inclination, and I'm probably doing myself out of a job here, but my inclination would be actually to go with, well, Open Embedded is my favourite at the moment. I tend to use that for my projects. LTIP's quite good. Buildroot has some good things about it. The main thing I have against Buildroot is that if you just use it in its vanilla form at least, it will use a UC-libc library, C library. And as I said earlier, I don't really like UC-libc that much. You can actually use Buildroot with an external toolchain, so you can actually use an angstrom toolchain with the Buildroot build environment if you really want it. But I'm not quite sure why you want to. So I would go with either angstrom or Open Embedded in most cases. Or possibly Android. But that's a different story. So those I think are, well, they're not all the choices obviously, but they are an example, a sample of the choices you have. I got a toolchain with my board. This is the biggest pitfall most people fall into, I believe. The thing is that most times these days when you buy a development board from whoever, they will bundle in a Linux toolkit. There'll be a little penguin on the website, and there'll be a We Support Linux link on the website. And you go to the download page and download something. Usually it is crap, quite honestly. Not always, but usually. The problem is that the guys doing this are basically hardware engineers, and they just want something that demonstrates that the board works. So they will generally put together some kind of Linux implementation that works on their board. But they are not going to tune it particularly well. They will give you particularly an out-of-date toolchain. Quite often they use build root to build the toolchain, so it will be UC-libc based. And so on and so on. And quite often they will not do any kind of updates, so once you bought the board, they kind of forget about you. So I very strongly recommend that in this case you don't use the toolchain that was given to you, but that you instead investigate the things I showed on the previous slides and put together your own toolchain, or, well, I don't really mean that, but use either a community toolchain or a commercial toolchain. That at least will have some kind of update policy, and it will be more robust. But I mean, as an example, I was talking to somebody last week who had bought an ARM development board from a very well-known company, and they were saying it's a bit slow though. It takes 2 minutes to boot up. I said, 2 minutes? You're crazy. And they were saying, how can we reduce that? We really need to. I want to get it under 30 seconds. And I was amazed. But that's the kind of thing you can get. And also that particular thing, we're delving a bit further, is using kernel version 2.6.18 or something, which is 5 years out of date, 4 years out of date, anyway, it's a long way out of date. So that's the kind of thing you can fall into. So, do not, and this is the big, I'll say it again, this is the trap most people fall into. Do not just take what you get with the board, or with the chip, or whatever. Quite likely it is not what you want. Okay, so we're going to be using a toolchain. It will be an angstrom toolchain. And the angstrom thing follows the fairly standard pattern. Most of these toolchains will install either into a subdirectory user local or into /opt. And then within that subdirectory tree, you'll find the cross compilers. Oh yeah, typically the cross tools have a prefix. So simply just type in GCC, you'll type something like ARM angstrom Linux EADI in our particular case, GCC. Now this prefix is different for every toolchain, but there will be one. And then also it will contain, excuse me, a bunch of header files and libraries. And so to make use of it, the simplest thing, in the simplest case, all you've got to do is to add the binary directory where these binaries exist to your path, something like that. And then you can just use the cross compiler to cross compile, for example, myprog.c. So in essence, it's as simple as that. In my description of the toolchain so far, which just contains binutils, C compiler, libc, and possibly a debugger, then all you've got there is an engine that can generate code for your target. But you can't really write very interesting programs using just that. Typically, you will want to add in some additional libraries. So in my example here, you might likely want SQLite 3, for example. So you will have to, if your toolchain doesn't already have SQLite 3 as part of its package, you will have to go and cross-compile it yourself. Now, I'm not going to go into great detail in this, but let me tell you, cross-compiling is no fun. So try and avoid it if you can. So, referring back to what I said earlier, try and choose a toolchain that has all the libraries, or at least most of the libraries you're going to be using, already available. When adding an extra library to your development environment, remember that you need not only the header files, you will also need the archives and the linker scripts, the .a's and .las. Well, actually you only need those if you're going to create static binaries, but you may want to do that. And of course you'll need the shared objects, the .so files, both in the development environment and also on the target machine. Right, I think I've said that several times, so I'll skip that. Finally on this topic, debugging. It's possible you have a bug in your system, so it's good if you have some support from your toolchain for debugging, which means not only that you'll need GDB, you will also typically need a GDB server, so that you can run GDB server on the target and then do remote debugging over a network or serial link. But also, I say ideally it should, I think I should get rid of the ideally, say it should, your toolchain should provide versions of the libraries with debug symbols, hopefully with down to the source code, lines of source code symbols. And it would be very handy if they gave you a nice, easy to use form, the actual source code, so that when you have a bug in a library, or you believe you have a bug in a library, you can actually step through the source code and see what's going on. And not all toolchains will give you that. Other goodies, well, there are many plugins for Eclipse, profilers, tracers, etc., etc. Okay, so that's the first, most fundamental element covered. The next thing I want to talk about is the bootloader. The bootloader is something you're going to have to, particularly for custom hardware, you're going to have to get hold of a bootloader to initialize your hardware. Do things like set up the SD-RAM, set up the memory map, set up the processor mode, initialize whatever peripherals you may need to load a kernel in. And typically these things can load usually kernel images, but maybe other things too, over Ethernet, or serial, or from an SD card, or from various other locations. Oh, and for some reason everybody wants a splash screen, so maybe it's useful if it supports some kind of splash screen. although really, if the bootloader is written efficiently, it shouldn't actually be present long enough for anybody to notice, or a splash screen to actually do anything. Look at that. This is just a comment really about the different flash technologies. With the advent of NAND flash in most devices, it makes storage very cheap and there's loads of it. But it has the downside that you can't execute code out of NAND flash. So what you normally end up doing is, many chips actually have a bit of microcode built into them, so they can actually read the first page out of a NAND flash chip, for example, and then start executing that. So you typically end up with some kind of pre-bootloader. On the TIO maps, for example, that would be a thing called xload. Little chunk of code, maybe only a few kbytes, just enough to be able to load in the main bootloader, which for example would be U-boot, and then that will load in the kernel. Okay, loading a kernel. This, after all, is what the bootloader is really there for. This means that you have to generate some kind of description of the hardware, which you're going to pass to the kernel. You will need to be able to load a kernel image from some storage device, such as NAND flash, and put it into the right place in memory. The kernel, when it loads, requires a command line, an ASCII string. So you see, you need some mechanism for specifying that string. So the bootloader will do all of these things, and then it will jump to the start vector of the kernel and set it running. There are several ways of passing this hardware information from bootloader to kernel. And just to give you an idea of what they are, I've just got a couple of slides on two of the most common, A tags and flattened device trees. So far as I know, well, the ARM architecture certainly uses A tags currently. I'm not quite sure exactly which other architectures do. But essentially it's just a linked list with a standard header and then various bits of information tagged onto it. So we have things like the size of memory and the start address of memory. The kernel command line actually goes in as one of these A tags, and so on and so forth. So essentially the bootloader will generate one of these structures and pass it in a register, R2 in actual fact, when it starts Linux up. Linux will then look at R2, register 2, and find all this stuff. So that's one way of doing it. Another more flexible, perhaps, way of doing it is to use flattened device trees, or FDTs. There's a lot more to it than what I have in this slide here. I'm just introducing the concept, really. But a flattened device tree is kind of a similar thing, except now we have a tree structure starting from a root, and then we have nodes like, for example, CPUs, and then for each CPU you have a node describing a particular CPU. And you can kind of generate these to your heart's content. Typically, in fact, you generate this as a text file, and then you feed this into both the bootloader and to the kernel. But it's just another way of the bootloader telling the kernel what it has, what resources it has.
Excuse me. Why does it say flattened? It's flattened compared to what? A hierarchical one, or what?
Well, okay, I mean, it's logically not flattened, but the format in which it's passed to the kernel is flattened. I don't know, they're flattened device trees. They're FDTs, that's all I really care about. So bootloaders. The one that is most commonly used, and indeed the one we'll be using today, is one called U-boot, or strictly speaking Das U-boot, because it's from these nice guys called Denks, German consultancy, and one of the things they do is the U-boot. They sponsor the U-boot project. U-boot has become very flexible. It's available on the major embedded architectures, and yeah, it's the one that I use mostly. Another fairly common one is Redboot, which actually is essentially a stripped down version of ECOS, which is a real-time operating system, which is part of Red Hat now. ECOS works actually on the same processor architectures, but it's, for whatever reason, it's not quite so common. Mostly you'll find Redboot on the Freescale IMX series. Freescale are very much keen on this. Intel Xscale, they're mostly Redboot based. And also, going back in time a little bit, the Cirrus Logic, the 93XX series, EPS, can't quite remember. They're a bit old now. So, on 3 ARM families anyhow. And so on, certainly on PowerPC, you'll almost always find U-boot and other things too.
Okay.
No. Yes?